Okay, welcome everybody. And yes, in this online world, we have to say good day to you wherever you are, whatever time of day it might be where you're logging in from. I hope you're all keeping well, staying safe and healthy. Now we've got a really interesting speaker and topic for today. It's about the spread of COVID, the physics of the aerodynamics rather of the spread of COVID through droplets. Our speaker is Swetaprovo Chaudhuri from the Institute for Aerospace Studies at U of T. Swetaprovo, please.
Thanks a lot, Professor Murthy. And thanks a lot for inviting me to this talk. It's an honor to be talking at the Phillips Institute COVID-19 Math Modeling Seminar. So I am Susceptible Chaudhuri. I work at the Institute for Aerospace Studies, University of Toronto. And today we are going to discuss constructing a COVID-19 disease spread model from the flow physics of infectious droplets and aerosols. And Saptoshi Boshu from Indian Institute of Science and Abhishek Shah from University of California, San Diego are the collaborators in this work. So what do we do? Where does our research focus lies normally? Now we look into the turbulent reacting and multiphase flows relevant to aerospace propulsion. So as you know that there is different kind of aircraft engines as well as rocket engines. And in the heart of these engines is the combustor. Now in the combustor, what is done is you inject the liquid fuel in a large number of droplets. I mean, the droplet sizes can range from anywhere between 1 micron to 150 to 100 micron. Okay, and these droplets evaporate and then they mix with the air and they react and release heat. And then that heated high pressure air can be used for basically generating thrust. Now, what happens is that there is strong turbulence and this turbulence interacts with flames. And we look into how basically flame interacts with turbulence, how fast they propagate under the impact of turbulence, and things like flame extinction, flame stabilization, and all aspects of them. Now, but what this is basically, this is essentially a multi-scale problem that involves turbulent multiphase flows and chemical reactions. Why I'm talking about this? Because we can say that, as I will show in next slide, that COVID-19 is also essentially a multi-scale problem involving turbulent multiphase flows, exactly same gas, liquid, and solid phases, as well as it involves chemical reactions, or you can say biochemical reactions. And we will show that the kind of reaction mechanisms we use here can be directly applied in basically modeling the disease spread as well. So from here on, I will talk about COVID-19 disease spread. Now we can say that the COVID-19 disease spread is essentially a multi-scale, multidisciplinary problem. Why is it multi-scale? It involves scales from the size of the virus, which is 120 nanometers in diameter, and it involves all the way, it involves scales from 0.5 micron to 1 millimeter, which is the size of the respiratory droplet at the time of its ejection. It involves respiratory sprays, which contains airborne and ballistic droplets, which these ballistic droplets can go about at max 2 meters. But the droplets that are ejected doesn't stop there, okay? Because these are airborne, these are very tiny droplets, and these droplets can basically spread along with the turbulence in the air, or they can just spread with the jet and the puff that is caused as a result of the cough or a sneeze, or even by talking, or even by breathing, and then they can spread. And these infectious aerosols can disperse and spread in clouds. And then people inhale these aerosols, and then that's why the COVID-19 is essentially an airborne disease. Now, before I go into this, what settles that the fact that the COVID-19 is an airborne disease? Now, if you look into the time scales, the settling time for a 100 micron droplet is about 10 seconds. Okay? Now, the settling time actually increases because the droplet evaporates, and it evaporates continuously. It basically loses the water, and then it basically gets to form a droplet residue, which we call a droplet nuclei. I'll come to that. But the settling time for a 1 micron droplet can be of the order of 300 hours plus. Now, the virus lives for the half-life of the virus, as has been proven from experiments in aerosols, can be anywhere between 2 minutes to 30 hours, depending on the local temperature, relative humidity, UV index, and so on and so forth. Okay, and of course, 120 hours is the mean incubation period, that is about 5 days. So you can clearly see that this large variation in timescales, the fact that the droplets can remain airborne for a long lot of time, and the fact that the virus leaves for comparable timescales makes essentially COVID-19 an airborne disease. All right, and then of course at the very largest scales you have the worldwide spread, which is, I mean, this is the longest flight distance. It can go from 16,000, 17,000 kilometers. So it involves scales, length scales from all the way from 120 nanometers to tens of thousands of kilometers at the disease spread level. And it involves time scales of the order of, I mean, even smaller time scales can be there because the droplet evaporation time scales are smaller, all the way from few seconds to few months. Okay? Now, then the question that we ask is that, can we construct a disease spread model that is how the disease spreads, not only by restricting ourselves to this to particular ACIR model, but can the ACIR model be built all the way involving these different phenomena that builds up to the disease spread? Okay, that is the question that we're going to ask, and we'll see that how far a progress we can make. And of course, it's inherent here that the fact that COVID-19 is a multidisciplinary problem, and that the discipline actually changes kind of with the length scales. I mean, this is governed by biology, virology, immunology. This is governed by droplet physics, evaporation, which is controlled by thermodynamics, species transfer, chemistry. This is governed by fluid mechanics. This is governed by aerosol physics, and this is governed, of course, by epidemiology. So it involves multiple disciplines, as it involves different kind of scales, length and time scales. So the question is the following. We have two specific questions in mind. That can we identify and quantify the relative importance of the different dominant transmission routes of the SARS-CoV-2 virus? What contributes most to the dominant routes? Droplet nuclei? What? And if we can identify the different routes, can we construct a disease spread model from the mechanics of these different routes that we have identified? So to that end, we start with the following thought experiment. So suppose we have a large indoor area. The indoor space is kind of air conditioned at typical temperatures, typical relative humidity. And we have a crowd, and each people in this crowd are moving in random directions. And at random, are basically moving randomly. Now, one person in this crowd basically coughs. And as that person coughs, that person ejects a plethora of droplets of different sizes, and those droplets are ejected in a gas cloud. Okay? And this gas cloud basically is ejected in the form of a jet. The jet transitions to a puff, because at some point of time the momentum source is cut off, and then the puff disperses in this crowd. So this is the basic framework that we are going to look at. And this is the problem, this is the schematic of the problem that we formulate. So this is the infected person, this red circle, and this infected person is this spray of infectious droplets of different sizes. These droplets are denoted by red, and after some point of time, the droplets evaporate, and as they evaporate, they do not vanish. They leave behind a droplet residue, which is basically a combination, a solid or a semi-solid matter, which can contain salt, proteins, mucin, surfactants, and the virus. And those droplet residues are denoted by blue. And these basically cloud spreads. And then we have these green susceptible individuals who are moving basically in different directions. And then if they cross this cloud, then they can inhale these droplets or the droplet residues, the aerosol particles, essentially, and they can basically get infected. And for the step is that this susceptible individuals, upon inhalation of these infected aerosols, becomes exposed, and this exposed after the incubation period becomes infected, and then they can recover or they can get diseased. So this is the basic framework that we are going to look at. So the objectives are the following: that first we need to estimate that if this susceptible individual crosses this droplet or aerosol cloud, what is the probability of infection? Okay, what is the probability of infection by droplets of the droplet nuclei? That is a droplet residue. And once we can identify the probability of infection, then can we estimate the infection rate constants and the corresponding basic reproduction number that can be used in a ACIRD model. Okay. Now, the probability of infection and the rate constants are not same things. The probability of infection goes into this rate constants that we will show. So, of course, it would have been very nice if there was a very clean set of governing equations that we could have solved to basically solve this entire problem. But unfortunately, due to this large disparate, due to this very large range of scales, and due to the involvement of these different disciplines, it's almost impossible to construct such a thing. Okay, you need to, if you are to do the entire simulation from the virus to the disease spread, you need to basically solve in a grid which is at the smallest scales can be of the order of a few microns, and at the largest scale can be of the order of tens of thousands of kilometers. So that is not possible. So the approach we adopt is the following. That is, we start with a coug droplet size distribution, which was experimentally measured from literature. We get it from literature. And then we feed that thing into a respiratory droplet aerosol model. Now, what this does is it solves the governing equations, mass, momentum, energy, species, for droplets of different sizes. And it gives us the evaporation time. It gives us the settling time. Now, of course, it is to be recognized that the droplets do not get ejected individually or isolatedly. A large number of droplets are ejected, but they are ejected in a gas cloud, as Borobio's work has shown. Okay. And so it is this respiratory droplet model cannot be solved in isolation. It needs to be coupled with the corresponding jet puff aerodynamics model. Okay. And this, of course, we need to include the information of the virus, because whether the droplets or the aerosols will be infected or not depends on the virus half-life. So we need to provide those inputs also. We need to provide the inputs of the virus lifetime. Extremely important is the viral load, that is the number of viral particles per unit volume of the liquid that is being injected. And we also need to include a dose response model that will essentially determine, and all this coupled will determine the probability of infection. Okay. Now then the probability of infection needs to be coupled once again with the jet puff aerodynamics model, because this now, once you get the probability of infection, you need to basically find out that is what is the frequency of this infected cloud, what is the frequency of collision of these susceptible individuals with this infected cloud, or with this infectious cloud. Okay, so that is a very important thing. So once we know the frequency of collisions or frequency of contact between the susceptible individuals with the infectious cloud, we can combine with the probability of infection, and that can yield the rate constants and the local basic reproduction number from this collision theory. Okay, and then we are all set to use these things into the ACIRD model. So this is the approach that we are going to follow. Now, what I will do in the following is that I'll just bring these individual models, jet puff aerodynamics, respiratory droplet model, and the virus half-life, etc. Please feel free to look into the papers for detailed description of this. But I'll more focus on the how to derive the probability of infection and how to derive the rate constants, and this are not from the collision theory. So, but first I will discuss these models quickly, and then focus on these in a more at a greater details. Okay. So first, this whole exercise will focus on estimating the probability of infection by droplets and droplet nuclei. Now, it is to be recognized that the conventions that we adopt, that at the moment of ejection, everything is in a form of droplets. Okay, these droplets contain water, these droplets contain salt, these droplets can contain protein, these droplets can contain surfactants, and of course the virus. And at the moment of the rejection, they can range anywhere between 0.5 microns to 750 micron initial diameter. Now, but the medical community at the following has now has put a cutoff about 100 micron, and the aerosol community, of course, has put a cutoff about 100 micron. And they say that below 100 micron, we call them as aerosols, and beyond 100 micron, we call them as droplets. But for this purpose of the talk, we use the convention that whatever contains liquid predominantly and can be defined by a surface, free surface, is essentially a droplet. Okay? That's the physics definition. And of course, these droplets, if it is 0.5 to 750 micron initial diameter, they can be both airborne or ballistic. The small droplets are, of course, airborne. As I have shown before, that a 100 micron droplet has a settling time of 10 seconds. So all the way from basically 100 micron and smaller droplets are basically airborne for a substantial amount of time. Whereas one that are above 100 micron and even larger ones can have sufficient momentum, and they can behave as they can have a ballistic trajectory, okay, which are more dominated by their momentum and the gravity. And so we model the respiratory droplets as a 1% salt water solution, 1% NaCl water solution. All right. And of course, the real respiratory droplet contains more components, but for the time being, we use this as the constituents, and we will show that this model, this surrogate model that we use, works reasonably well when we compare the model outputs with the real saliva experiments. So this two-component model basically works well. And then the convention is that the droplet nuclei are those solid and the semi-solid residue that are left post-droplet evaporation. And we'll show that the size of this droplet nuclei is typically 1/5 to 1/6 of the initial droplet diameter if the relative humidity is beyond about 80%. If the relative humidity is very large, about say 90% or 100%, then the droplets does not evaporate at all, and they continue with their initial size. So in this whole discussion, temperature, relative humidity are very, very important factors. And we need to basically, and that emphasizes the importance of having a very robust droplet evaporation and settling model, because depending on the temperature and the relative humidity, the evaporation time and the settling time of the droplets will be governed by temperature and relative humidity. And not only that, the final equilibrium diameter of this solid or the semi-solid residue will depend on the relative humidity. So it is very important to have a robust droplet evaporation settling model to be included in this approach that we are doing. Okay, so we say that this is known, as I have said before, from the work of Borobia, that droplets are ejected in a turbulent jet that transitions to a puff. Okay, initially you have a lot of momentum through which sustains the jet, but after the puff stops, the source of the momentum is cut off, and as a result of that, the jet transitions to a puff, and then this puff expands. And of course, this whole puff expands and the jet also increases in diameter, because as the jet moves, it continually entrains air. Okay, and this continual entrainment of air actually dilutes the concentration of the droplets and the aerosols that is present within the jet and the cloud. or the puff. So this is very, very important. This continuous entrainment of air that happens, and that reduces the concentration of the aerosols within the cloud. In this work, we do not consider effects of turbulence and or ventilation. They are actually coupled, but we are in present work, we are actually including these effects also. And then we say that the infection occurs when a certain number of virions are inhaled upon collision of susceptible individuals with the droplet or the droplet nuclei cloud. Okay, so as soon as a person comes in contact with the cloud, okay, the cloud is expanding, people are moving, and they can inhale a certain number of droplets or virions. And when they inhale a certain number of virions, then there is a certain probability of infection. And this comes from the dose response model that we will use. So first, is this the top part of my slide visible?
Yes, we can see it.
Okay, great. Okay, so this is the droplet evaporation and the desiccation model that we're talking about. Okay, so first the droplet evaporation model. This is fairly detailed. So we work with this surrogate cough droplet, that is 1% sodium chloride cough droplet, which is evolving in the exhaled air. But please remember that these droplets do not evolve isolatedly, they evolve in the exhaled air. So their surroundings is governed by the output of the jet puff model that I'll show how the coupling occurs. So of course, this is the mass flow rate of the water, that is the rate at which the water leaves the droplet surface due to evaporation, and that is given by this formula. I'll go over this quickly. I'll not go into the details. This is the density of the vapor, this is the diffusivity, this is the droplet size, and this is the mass transfer number. The mass transfer number is essentially the difference of the mass fraction of water on the droplet surface and the mass fraction of water or water vapor on the gas. Okay, and this is 1 minus L1S, Y1S, that is the mass fraction of the water vapor on the droplet surface. Okay, and this mass fraction of water, if it was just pure water, then things would have been simple. But now this droplet also contains salt. Now, as the water content in the droplet is reducing, the salt concentration is increasing. And now we have to basically take into account the vapor pressure on the surface. So this mass fraction on the water on the surface is controlled by the vapor pressure of the liquid on the surface, and that is controlled by the local temperature and the mass fraction of water. The mass fraction of water itself can be defined as 1 minus the mass fraction of the salt, and this basically comes from the Raoult's law. That is the vapor pressure is basically determined now by Raoult's law, because your concentration of salt is increasing in the droplet, and that, because of the increasing concentration of the salt inside the droplet, that actually suppresses evaporation because it reduces the vapor pressure. Okay? And this is the vapor pressure. This is the mass fraction of water in the far field that is in the gas. It's just in the near field gas. I'm sorry. This is the mass fraction of water on the near field gas, and this is once again controlled by the relative humidity of the exhaled air. Okay, and then we can do a simple scaling by which we can couple the temperature of the gas and the mass fraction of the gas with the momentum of the gas, because we can say that the Prandtl number and the Schmidt number, basically the ratios of the corresponding diffusivities and the viscosities, and those are close to 1, and as a result of that, this can be better. And this is verified experimentally also. Now we need to still know the temperature of the water on the droplet surface, and that we can obtain by solving the energy equation for the droplet temperature. And we assume that the droplet temperature is homogeneous throughout the droplet volume, and that's a very good assumption. Okay, so this is the equation that we need to solve, and this yields the temperature. Okay, the Raoult's law yields this mass fraction of water on the surface, which is also a function of the mass fraction of salt on the surface, and from that we can get the mass fraction of water on the surface. We get the mass fraction of water in the near field gas, and we can put this in, and we can find the evaporation rate of water from the droplet. Now, the mass fraction of the salt, which is the mass fraction of the water, is basically 1 minus the mass fraction of the salt. For that, we need to basically solve a species balance equation, And now we say that after a certain threshold, the salt essentially crystallizes. And this is basically the one-step crystallization chemistry that we include. So all this yields basically the mass loss of the mass flow rate of water from the droplet surface. And that is basically needed to obtain the droplet evaporation time and the drying curve of the droplet. And then the droplet motion we can basically solve using the momentum balance. This is essentially Newton's law. Balance of, this is the MA term, the rate of change of momentum, and this is basically the drag force that acts on that. Okay, this is in the x direction, and using the Stokes settling velocity, we can find out the time for settling of the droplet. I'll not go into this in details, as I said previously, and just show how this works. Just give a glimpse. The respiratory jet puff model, once again, initially the exhaled air is a jet, and that we can show that using, once again, mass balance, momentum balance. We can show that initially the diameter of the jet initially scales as t to the power of half, and once the momentum source is cut off, the jet transitions to a puff, and then the diameter of the jet, the diameter of the puff evolves as t to the power of 1/4. So by combining these two, t to the power of half and t to the power of 1/4, we get the diameter of the jet, the position of the centroid of the jet of the puff, and the position and the velocity. And this is required. This is coupled to the droplet evaporation model. Okay. So this is the validation of the droplet evaporation model. Now we do experiments in a contact-free levitated setup. So we basically levitate this respiratory, this actual saliva droplet in this acoustic levitator at a given condition, and then we measured basically the drying curve, the normalized droplet diameter as a function of time. So this is the experimental result for a real saliva, human saliva droplet of initial diameter 550 micron, and this is the model prediction. Okay, this does not involve any jet puff, and we see that after a certain time a plateau is hit, because now what happens here is that the mass fraction of water has reduced because the salt mass fraction has increased very much, which suppresses the evaporation. So this plateau continues, and then after some time the mass fraction of salt has gone up so much that it has crossed certain threshold, and then the salt kind of crystallizes out. Okay, and as a result of that, now evaporation can again proceed, and the droplet can get almost dried. And certain relative humidity, the droplet will not be dried. Okay. So this basically validates our choice of the sodium chloride water droplet evaporation. Of course, there is certain difference, about 15%, but we live with that for this work. Now, this is a very important plot. So once our droplet model is obtained, we can find out the evaporation times as a function of the initial droplet diameter. So this is the evaporation. This is the initial droplet diameter, and this is the evaporation curve. It continuously increases, whereas the settling time, as found from the Stokes settling velocity, which is a function of the instantaneous diameter, continuously reduces. Okay, so this increases, the evaporation time increases, and this continuously reduces. Okay, now there is a jump in slope because at the very large diameters, the droplet settles in its droplet state itself. But beyond certain, after the most of the droplet has evaporated, now it is basically the dried droplet nuclei, and the size of the dried droplet nuclei and its state are different from that of the droplet. So that's why we get a difference in the slope here. Okay, so what we get out from this is that at any instant of time t, we can know that what is the fraction of my initial droplet distribution has become a droplet nuclei, because anything above this curve, this blue curve, has become a droplet nuclei, and anything below this blue curve still remains as a droplet. So we can know at a particular time that what fraction of the initial droplet distribution that was ejected has become droplet nuclei. It's essentially this part all the way from 0.5 microns. So if you look at this time, that is 7th second. So here, all the way from 0.5 micron to about 25 microns has become droplet nuclei, whereas from about 25 micron to 150 microns still remains as droplets, because large droplets need more time to evaporate. Okay, and what fraction has settled? So this becomes very important in telling us at any particular instant of time, what is the state of the cloud? What is the state of the cloud, of the cough cloud that was ejected? Okay, that we can say from this curve itself that this is the state of the cloud. Okay, so and also important to note here is that the virus half-life is somewhere here, about in the 900 seconds. Okay, about 950 seconds at this temperature and relative humidity. So this clearly tells us that the large fraction of the nuclei have which are airborne, has remained infectious. Okay. So now we go into calculate the probability of the infection, and we start with the PDF of the probability density function of the ejected droplet diameter. So this is we can approximate the initial droplet size distribution using a log normal distribution. So this is the log normal distribution. We use results from Duguid's paper. Okay, and the cumulative number of virions in droplets between sizes D1 and D2 is given by this formula. So the total number of virions or virus particles between sizes D1 and D2 is a function of this PDF. Okay, it depends on the total number of particles of the droplets being ejected. It depends on the viral load. This is a very important parameter. The average viral load can be 7 million copies per milliliter, and the maximum viral load can be 2.35 billion copies per milliliter. Okay. So this is the cumulative number of virions between sizes D1 and D2. The number of virion particles that can be inhaled by the droplet route, okay, can be is a function of basically once again all these things: total number of virus particles, viral load. It's a function of the size of the inhalation volume, or which we convert into basically hemisphere, and this is the effective diameter of the hemisphere. The size of the cloud, the number of breaths per unit time, the relative velocity with which the people are crossing the cloud, okay, and the sigma d once again is the diameter of the cloud, and this is to get infected by the droplet route. We have to basically find the droplets, and these droplets are between, at this particular time, can be between D1 and D2, whereas D1 and D2 are basically these two limits. So because at any particular time, only between D1 and D2, you will find droplets. So likewise, we also calculate the number of virion particles that are inhaled by the droplet nuclei route, and the nuclei route can be anywhere between 0 to this Dn, whereas this Dn is basically given by this limit if the time we are considering is less than the droplet maximum evaporation time, or by this limit if the time we are considering is greater than the settling time. Okay, so anything here is basically droplet nuclei, anything here is droplet, and this equation basically, these two equations basically find out first the number of virions available from the droplet route, and then compute the number of virions that can be inhaled if we just inhale a certain amount of volume from this large droplet cloud or this large droplet nuclei cloud. Okay, so this is the formula that we use, that we develop for basically calculating the number of virus particles inhaled by the droplet nuclei or the droplet nuclei, or the droplet of the droplet nuclei route. Now, one important parameter is this factor, this psi, or this psi, that is, this gives the number of the fraction of infectious virions that are available, and this is a function of temperature, ambient temp. This is a function of time, temperature, relative humidity, UV index, and it can be modeled using this half to the power of T by the half-life of the virus, and we can get this number, this T half, from this website, which is essentially is based on this very, very important paper where this infectivity rate constants are provided. So they made basically aerosol experiments. And why does a virus survive inside the nuclei? Now, this we learn from this seminal works by Lindsay Marr's group. Basically, the virus gets distributed, gets entrapped inside the nuclei, inside the droplet nuclei, and they get kind of frozen. Okay, and as a result of this, whereas if the droplet remains as is, that is almost in its droplet state, then the virus can remain infectious. Okay, so as a result of this, this half-life has a kind of a U-shaped curve as a function of relative humidity. And this information is basically included in the model that we have just shown. We also did experiments with the salt crystals, and we see that the distribution is essentially similar. So most of the virus gets entrapped inside this droplet nuclei, but once they're entrapped does not mean that they become non-infectious. Once they're entrapped, it means that they're kind of frozen, and once they come out and interact with human cells, lung cells, etc., they can still again regain their potency. Okay, and this was proved by this very important paper by Lipinski, where they basically isolated this aerosol particles at a reasonably large distance from 2 meters and 8 meters, and then they could culture these virus particles. Okay. So now, once this number of virus particles that are inhaled by the different routes are settled by this, as I've said, by these formulas that we have developed, once they are done, we can basically estimate the probability of infection. Okay, and that is given by this formula. It's essentially a Poisson distribution. So the probability of infection by the expiratory event alpha and the vector beta, that is, expiratory event can be cough, sing, sneeze, talk, etc. The beta can be droplet, nuclei, or fomite, and that is given by this formula. This is essentially the dose response model that was developed by Haas. And then we can find out the total probability of infection if we sum over the different vectors, the contribution of the virus particles inhaled by the different vectors. And that is what we have done. Okay. Now, the MID, the minimum infectious dose for SARS-CoV-2 is unknown. So what we do is essentially we do a variation of these parameters to see what kind of response we get. I'll come to that later. So these are the results. So this is the initial droplet size distribution that is ejected from a cough. Okay, and this is the number of virus particles at those sizes. So this is the initial size, and this is the PDF. Okay, and this is done at these particular conditions: ambient temperature 21 degrees Celsius, relative humidity 50%, and this is the exit state of the gas that is being exhaled. And we can clearly see that this is the histogram of this droplet size, sizes. This is the initial size, and it shifts to the left because of droplet evaporation, and it also shifts to the left because the droplets settle out. So within at time t equal to 0, this mode for this histogram was about at 13 microns, but within about a few seconds, within about tens of seconds, it shifts to about 11. It shifts to about 2.5 microns. So we can see that there's a very fast, reduction of the droplet size is an important phenomena that is happening here. Okay. Now we can estimate then the probability of infection. The red curves corresponds to the probability of infection for the droplet route. The blue is for the nuclei route, and here we plot the probability of infection as a function of time. And here we plot the same thing, probability of infection for the cough event for the different vectors as a function of distance. And clearly, the probability of infection reduces as we move in time or in distance. And this is because the droplets are evaporating, and more importantly, the droplet cloud or the jet is diluting because it is entraining air. Okay, this dilution is a very important effect. So this and after some time, the droplets essentially evaporate and they vanish. But of course, they do not go away. They leave behind this droplet nuclei. Okay, So these droplet nuclei, now the probability of infection by the droplet nuclei picks up, and we now see that they continue. But clearly the probability of infection by the droplet nuclei is always smaller than that of the of inhaling the droplets. And that is because by the time the droplet nuclei are developed, the puff has diluted to a reasonable extent. The size of the puff is very large. So the concentration of the nuclei inside the puff is small. So that is why the probability of infection is less if one crosses a droplet cloud versus a droplet nuclei cloud. But we will see that this does not mean the droplet nuclei contributes less. Okay, so this is an important distinction. So next we plot the different the probability for the different droplets with including different cutoffs. So here we provide cutoffs, that is, if we can prevent the ejection of droplets beyond these particular sizes, okay, beyond 150 and 10, how will the probability look like? So we find that if we cut off at 100 micron, nothing changes much. But if we can cut off the droplets beyond 10 micron, then the probability reduces very sharply. So from this, we can conclude that that the probability that the droplets with the initial size between 10 to 50 micron contributes most to this probability of getting infected. Okay, we can see that the probability of if the cutoff at 50 micron also is very large. Okay, so now can we estimate the rate constants and the from SEIRD model? So we can write the SEIR model as the following, that in a form of a chemical reaction mechanism, we can say that S plus I becomes E plus I, that is susceptible plus infected when they come in contact and they inhale those aerosols, becomes exposed plus infected, and that corresponding rate constant is given by this K1 alpha beta. Now what is K1 alpha beta? The K1 alpha beta is dependent on both the respiratory event as well as the corresponding transmission vector. So we can break up this K1 alpha beta into all these different things: breath, cough, sneeze, stop, and droplet nuclei fumite, and these are all the different rate constants. Okay, and then of course this is standard. The exposed becomes infected. The infected becomes either recovered or deceased, and these are the different fractions. So we can basically solve this whole thing. Okay, this involves several equations, like as we do in chemical reaction mechanisms, and we can solve this whole thing as a form of this differential equation that immediately comes from the previous reaction mechanism, and we can obtain this can form our from the whole disease rate model. But then the question is that how to estimate K1. Okay, now we can estimate K1 using by adapting the molecular collision theory. Now, suppose in the unit volume we have Ni and Ns number of infected and susceptible individuals. Okay, so in a unit volume. So then a collision will occur in unit time if this susceptible individuals would lie within a volume which is given by pi times sigma ds square. Sigma ds square is sigma d is the puff diameter, and sigma s is the diameter of the inhalation volume, and this is sigma ds is essentially the sum of these two things. Okay, so this is the sigma ds square, and this is the relative velocity, the vds. So the collision will occur if susceptible individuals basically lies in this collision volume. The collision volume is essentially the volume swept by the cloud in unit time. Okay, now since we know the number density of these infected and susceptible individuals, essentially the susceptible individuals, so we can find out the total number of collisions just by finding out the total number of susceptible individuals that will lie in this collision volume, and this is given by this. Okay, but all collisions or all contacts will not result in infection, so that is why it is multiplied with this probability of infection. Okay, so then the total number of infections per unit volume per unit time is given by pi times sigma ds square times the relative velocity times the probability of infection for the respiratory event alpha and transmission vector beta times the number of infected individuals, number of susceptible individuals. Okay, so then we can generalize the rate constant by basically averaging over the time that is instantaneous. So This is basically the average of that. And we can find out the corresponding rate constant for the droplet. This is the K1 alpha D gamma. Gamma we can include a location parameter also. And for droplets, we only need to integrate between 0 to tau D, whereas tau D is the evaporation time, the max evaporation time. Whereas we can find out the rate constant for the nuclei. Nuclei can persist almost for an indefinite amount of time, and basically we need to integrate from 0 to infinity. But for practical cases, because the P probability goes to almost 0, we need to integrate only up to a point where the integral converges. Okay, so this is the rate constant from the droplet route, and this is the rate constant that we get from the nuclei route. Okay, and with the total rate constant is just the sum of these different parallel parallel routes, and so we just need to basically sum over this. Now here is the result. That is, if we consider this ambient temperature at 21 degrees Celsius, 50% relative humidity, and we do all the calculations based on the formulations that we have shown, the rate constant by the droplet that we see is this value, 0.018. The rate constant by the nuclei is almost 15 times larger. And we can find out based on based on this rate constant, we can find out the basic reproduction number also in this state, and this is this value. Now remember, the probability of the droplet of getting infected by the droplet was much higher than that of the corresponding nuclei. Okay. Now, but the rate constant contribution by the nuclei is much, much higher than that of the droplets. And that is because of two things. That is because, number one, the size of the cloud which contains the droplet nuclei is much larger. But more importantly, here we are integrating over a large amount of time. So the chance of getting the contribution by the nuclei is much larger because of the persistence of the nuclei, whereas the droplets only persist for a small amount of time. Tau D is much, much smaller than this by the time for which the nuclei persists. And as a result of this, we can clearly see from here that it is essentially this droplet nuclei, which is essentially aerosol particles, that contributes overwhelmingly over these droplets, even though the contribution to the probability by this is large. Okay, and we can clearly see as we reduce the temperature, because of this longer survivability of both the droplets and the droplet nuclei, these numbers go up, and the R naught basically also increases. Okay. So this can include the effect of temperature also, and the effect of temperature is very much important because the virus survivability is a strong function of temperature. And of course, it's a function of relative humidity and UV index also. Okay, so this is just some simulations we can just do with the ACIR model, and it shows that it just works perfectly well as a standard ACIR model would do. And then we can also estimate the basic reproduction number by this basically the ratio of the different rate constants. And then we can find out the rate the basic reproduction numbers if we cut off the droplets at different sizes. And that is, if we can prevent ejection of droplets at certain sizes, what would be the basic reproduction number, and how does it vary with the different viral load? Okay, so we can clearly see that for the viral load, the average viral load is somewhere here, whereas with the largest viral load, it can really go off the charts. And how does this reflect? Now, of course, with if we plot the minimum infectious dose, that is for a 99% chance of infection probability, and on the x-axis, and the basic reproduction number on the y-axis, for the average viral load, we get this curve. Okay, but for the max viral load, we essentially get this curve. And of course, this basic reproduction number is, of course, must have a distribution, because the viral load also has a distribution among the entire population. And we can clearly see that it can follow a population something like a PDF, something like this. So here I plot the PDF essentially. Okay, and the MID can vary. The minimum infectious dose can vary due to several reasons, due to reduced immunity, due to introduction of new variants, and all these sorts of things. Okay, and we can generate this curve basically for any temperature, any relative humidity, any condition. Okay, so that is what we are trying to do here. That is, for at any condition, can we generate the basic reproduction number for these things. Of course, it includes several other things like population density, etc. also. So now we are almost coming close to this talk, close to the end of this talk, and we can summarize. So what we have done is we have modeled droplet settling evaporation and desiccation in a cuff jet to calculate the infection probability. All right. And then we have combined it with the collision frequency between the droplet cloud and the susceptible individuals, and combine that with this probability of infection to estimate the basic R naught, the corresponding R naught. And from this collision theory, we developed this SEIRD model. Okay. And this can be generalized to any expiratory event. All we need is basically the input in terms of the droplet size distribution, input droplet size distribution. So, and that is available. We can use the input droplet size distribution for cough, sing, sneeze, talk, breathe, anything. Okay, so for any of this expiratory event, we can find out the probability and the basic reproduction number. Now, for this present case, we have done it for cough, and we find that this droplets with 10 to 50 micron have the highest infection probability. But by the time they infect, okay, they could be 1/6 of their initial size. So it's essentially they could be infecting at 1/6 to 1/5 of these numbers. So by the time they infect, they could be about anywhere between 2 micron to 10 micron. Okay. And the probability by the droplets is very high near the source. The probability of getting infected if you cross the droplet cloud is very high near the source, but decays soon after. Now, the aerosolized droplet nuclei, despite their low instantaneous probability of infection, they dominates in contributing to the R0C. And that is because of the large lifetime of the virus and the fact that the virus can remain potent inside the droplet nuclei, and that the size of the cloud, the number of people that the cloud can infect is much larger. Okay, and the fact that these aerosols can persist in the air for a long, long time. And we can show that preventing injection of all droplets beyond 5 micron could yield an R0C about 1. But this is only for the cough droplet size distribution that we have done. And we have also assumed that the viral load is uniform across all droplet sizes. So what is the next? What can we do next? We can, of course, make these individual models or the submodels much more rigorous. We can validate them further with experiments. Okay. We can add new modules in the form of ventilation, which you have not considered. But more importantly, this is SEIRD model is developed on one particular location. And we can, given the certain inputs, okay, that can be available from different databases, we can basically obtain the R0C for specific conditions, different indoor conditions. And from that, we can either generate a distribution, or we can plug this into a network model, okay, or a mobility network model, and we can basically use this towards practical disease spread model. So these are the next things that we have in mind. And acknowledgements, several people, definitely to Professor Lindsay Marr. I mean, her works and her discussions, advice has have a profound impact on what we have done. Professor Balachandar from Florida, Professor Kasi Butler from Duke, Eberhard Bodenschatz from Max Planck, Professor Menon from Ashoka and ICMS, several colleagues and advisors for their encouragement and support, and the award from UTIAS. So thank you very much. I'll be happy to address any questions.
Thank you, Swetaprovo. So I think there are some questions, but before maybe John Hong, is it okay if I ask the first question?
Yes, please.
So interesting thing, suppose I had multiple droplet clouds and there's interference in them. How does that affect your dynamics?
I mean, if you say that the multiple droplet clouds remain infectious.
Yeah, and is there some this is a density that you have to integrate over or something? Is it like there are multiple events happening in a certain volume of space?
Okay, so I mean, if they are not infectious, I mean, there can be two conditions. That is, we have one infected cloud and other not infected cloud. So in that case, the non-infected clouds will affect the dynamics of this by several effects through basically turbulence. and to dilution. So we can include all those things. And when we say ventilation, so this multiple people moving around, their exhalations, all this will add to increased turbulence, and increased turbulence will lead to further enhanced diffusion of this cloud. So this cloud will then diffuse faster. That is one effect that we can definitely think about. But if you have multiple infectious cloud, then its situation becomes complicated. And then also I believe we can address this, but we have to basically consider what you said, interference of these clouds and the total number of virus particles that would be integrated over all these clouds. But it can be done.
Right. And even if it's not infectious, I mean, the turbulence is a nonlinear phenomena, right? You'd have to deal with that.
So what we can deal with is basically we can model it using a turbulent diffusivity, which can be a function of your ventilation rates and a function of the people moving around, etc., and all these things.
Okay, so I think this is really, really interesting and important work because right now, as people think about the reopening of society, we may look at what we have at hand, namely public health measures such as masking and so on. We may look to vaccines, but then there are still public spaces where these things are not practical. As masking, for example, is not practical. And so ventilation is going to be a serious issue in terms of our return to normal. So these kind of models, I think they're very important. So it's very interesting work. I'm glad you guys are active in that. Good. Now I think Tom, you had a question.
Yeah, but also Atasha, I want you to hold on, and we'll definitely give a chance to ask questions.
Yeah.
Shall I jump in?
Yes,
it's Tom here.
Go ahead.
Yeah, fascinating talk. Thank you very much. I love the preamble with the multiple scales going from seconds and micrometers to thousands of kilometers. Just to go even more microscopic, I've been thinking a lot about the Haas dose response, which is sort of imagining the virions inside the body. Could you say that if you inhale nuclei, what you call nuclei, would that land in the tissue in a different way from droplets? And so with the rate, that R in equation 17, that R factor, would that be different for nuclei versus droplets?
Yeah, great question. It can definitely be. In this case, we do not consider them to be different. I don't think that is known sufficiently well yet, that what would be if the dose response curve would be different for droplets versus nuclei. But it can definitely be different. But in this work, we have not considered them to be different.
Yeah, so mathematically, the exponential function has wonderful properties, but I sort of think with an immune system acting on the virions when they enter the body, that exponential curve actually could be, it seems to me, quite a different shape from that. I've been working with this problem, and the exponential, I do know it has some really special properties, but I wonder whether it's really true. But anyway, I thought it was fascinating that you're linking this scale to the physics of the aerosols and droplets. But I just would. So the in-host, what happens to the nuclei and droplets in the body is then a very interesting question. I wonder if you'd comment on that.
Yeah, definitely that's a very important question, but yeah, I cannot comment on that. I mean, this is extremely important, as you point out, that because this couples the whole infection with the rest of the physics that is happening. But I think this is essentially, this kind of dose response model is the state of the art. I don't think, at least mathematically or physically, it is known beyond this kind of a model to integrate the physics with the physiology, I would say.
We need the in-host people.
Yeah. So this goes into basically the domain of immunology, and which I don't know anything about. So I cannot go further than this equation, to be honest.
We'll try to find an immunologist to have a pair to generate further discussions on this.
Yeah, of course.
I would like to really, Natasha, if you can ask, unmute and ask a question directly.
Sorry, who's that?
Okay, so so this is a student, a grade 9 student.
Oh, Artash.
Atash, and he wants to thank the speaker for a very fascinating presentation. And he is asking, he's curious to know if your model can explain the disparity in infection rates between different countries, especially countries with warmer and colder temperature. Which parameter of your model could account for this difference?
Oh, that would be, I think initially we were thinking about droplet evaporation and all these things, but digging more into this, I think the most important parameter that governs is this one, is the virus half-life.
Mm-hmm.
Okay, this is the most important parameter that probably governs why the infection shoots up in winter times, especially indoors where the relative humidity can be very small, versus in warmer countries where the temperature is higher. Of course, you have to take into account that the ventilation rates in warmer places, not necessarily warmer countries, are also much higher. I mean, in winter time, you close the doors and the air kind of circulates inside, so that reduces those things also. But in one word, in my understanding, it is this virus half-life. I mean, you can see here that at 20% relative humidity, the virus does not almost decay. This is from the actual data for SARS-CoV virus. It only decays at 40 degrees Celsius. Okay, so it almost stays here. Whereas if the relative humidity is 70%, it goes up here. So and even at the same relative humidity, even at the same temperature, even at the same relative humidity also, the temperature has a very big effect. So I think this is the most important factor.
So is there a role for the, viscosity? I mean, if there's high humidity, is it the half-life, or is it just simply that the thing can't move?
What happens is that I think, once again, the experts, as I showed, the Professor Linsimar is the foremost expert who can answer this kind of questions. But in my understanding, what this U-shaped curve results from the fact that if the relative humidity is very small, then the droplet kind of quickly evaporates and it leaves behind this droplet nuclei, and the virus remains frozen there. So there is nothing to basically deactivate it. On the other hand, if the droplet remains as is, as very high relative humidity, when the droplet does not evaporate, then also the virus can sustain well within the droplet. But in these middle relative humidities, what happens is that the droplet loses water, but the protein mass fraction kind of increases. And the virus probably does not like that protein. The protein is kind of responsible for deactivating the virus, and that results in the deactivation of the virus in this kind of mid-relative humidities.
I see. Interesting, very interesting.
Thank you. We do I do have questions, but I think the time is running out. Maybe I should take the opportunity first of thank the speaker again for coming to the Fields Institute, and this is fantastic talk. Really in the heart of what Fields is really trying to bring together. So we will find other opportunities to bring you again to this institute, and again on behalf of the institute, and Kumar is here, and on behalf of the task force, I want to thank you again and thank all the audience today.
Thank you very much. It has been a great pleasure and honor to speak in this audience, and thank you for inviting me for this talk. Thank you.
Okay, so see you everybody next week, next summer. Bye.